All right, I think we'll go ahead and get started. I know a few more folks will be joining us soon. So as always, I'd like to open up in prayer. Do that. I'll give a few headlines, intros, and then we'll get into it. So, dear Heavenly Father, Lord, thank you very much for the chance to be working with these students. I pray that you would bless them as they're learning the skills that are going to help them to propel into really good careers. And I pray that you would help them in that endeavor. Also help them with their spiritual formation, Lord, as they get a chance to be studying scripture, to be getting a better sense of the theological concepts we want to draw from that, and how to have interesting and creative ways for faith integration that they can do in the future. In Jesus' precious name, we pray. Amen. So once again, I want to apologize for last Thursday. Some of you were able to rejoin, and we got fiber in our house, and so we had to really rework everything we had. And I thought I had a very stable configuration, and it turns out that that wasn't the case. Actually, today I'm getting the fifth router that we've tried, and so this one should be does about everything. And I'll try and kind of integrate that into some of the things that we talk about. We're going to be continuing our conversation on memory. And so, and I'll bring up a little bit about, it's the idea that I'm thinking about is flash memory. And so what happened that the manufacturer, Netgear, talks about doing a factory reset and then loading your configuration again. So literally you're flashing the memory. And so if there wanted to be updating the firmware, that's an example of where you flash is something that it maintains its state once you've loaded in. And we're going to be talking about a couple other examples of what that's like. I see some of you have brought in your kits. And so if you wanted to pull that out, if you want me to look it over with you, but we're also, that's when we can do it face to face on Tuesdays and Thursdays. Is where I have all of my stuff at home. It turns out when I was in my office, we have like a shared area for storing stuff. I found this this board here, and for in case some folks are online, I'll turn on the video just to give you a sense of what this is. I'm not sure. Okay, this is like a larger size of these wiring boards. And so I'll just explain a little bit about it. So instead of just having one row of things, which you have, I know when I was looking at David, you had like a smaller one. The one I was showing you on Thursday was like about this length, but this actually has two of those. And so it was actually a little bit larger, and that gives you an idea of what you can do. Having these kind of terminals can be one of the ways that you can have an external power supply, and then you could route this on to somewhere on the board. I'll go pass this around the room if anyone wants to take a look at it. If you already have your kit, this may be something that you won't need to be looking over too much. But this just gives you an idea of some of the hardware and things that are there, which are kind of cool. So what are we going to be talking about today? I'll go a little bit through our greatest hits for this section. And I'm trying to point out like some key things that are things that caught my attention. I was going through some of this material over the summer. And so you could easily come up with something a little bit different. But one of the things that I got about this first chapter in this section of the computer system is you can have these virtual point-to-point connections, and PCIe is an example of one of those that is something that I've used. And what we're trying to do in this course is kind of going into the kitchen, if you want to use a cooking analogy, and see how things are made, rather than just having it, you go to a restaurant and they give it to you. There's other ways of looking at these types of things. I had a hard drive crash, and I'll start to talk about that a little bit more. But one of the things I mentioned was that the read and write time for memory isn't the same. Sometimes write or read can be a little bit faster. And so those are one of the characteristics that might be something that you hadn't thought about. And when you buy a hard drive, like we talked about cache the last Tuesday, and so we get that same kind of thing, even in a hard drive, because they wanted to try and make sure that you access information on that hard drive as quickly as possible. And so statistically, you're not always going for new information. They know that the general way, thank you, of how information is retrieved. And so the most recently things that you retrieved is what they make available. So even in something like a hard drive, they do that. And I may just pull up some of the specs for this hard drive. It's actually a designed for a server, and we have a home server. We back up things online, but we also do things with a local server. And so that is what we got a chance to be talking about last time. And so let's just go through some key points in the greatest hits section, and then I'm going to get into talking in more detail about internal memory. So Stalin does a great job of breaking things down into what we have for a computer. So you guys all have heard me use the term the von Neumann architecture. And so how many elements are in that? Three? Okay, good. Anybody have an idea what one of those three are? Yeah. Yeah. And so, and then Stalin kind of creates a fourth one, and just how you wire those things together. Sometimes I usually just group that together with the IO. We got a chance to see that. Now, when I put in a new internal hard drive, I'm going to be looking at the insides of my server. I actually have some of the manuals for replacing things, and maybe I'll show that in one of our future sessions. We had a couple of things that we talked about, just looking at the architecture, and this is just an expanded view of that. We talked about the general characteristics of operation in a computer, the fetch execute cycle. When we get into the central processor unit, we're going to get into that in more detail, but it will come up in a couple other places, but it's nice to just get a familiar introduction to that. We talked about this pyramid of memory, of going all the way from very slow, like a magnetic tape, to a hard drive, a magnetic disk, and then all the way up to what you have in the CPU, that it goes from slower to faster. We talked about that there's a distinctive difference between the memory access statistically, the way it goes for instructions versus getting data off a hard drive. Those are some things that are there. We talked about caching, and something that is not intuitive, but now you guys are getting a little bit of insight into that, is having multiple layers of cache actually help. And so it's common for a lot of places where you have 3 levels of cache, and there's different ways of implementing that. And so we talked about that in an overview fashion last Tuesday. And then in this chapter, this is where we get into some of the specifics of memory. Maybe I'll start with this one, and I'll have a chart that gets into some of these acronyms, like DDR DRAM, like DDR4 DRAM. That would be something, if you were to buy memory for your computer, that's an example of some of the things that you're going to have to be aware of, at least in call it Ed or Bob or whatever, but that has a specific meaning, and we'll get a chance to talk about that a little bit here. So, dynamic RAM, and I'll have a more detailed chart when we get into the focus, the detail of the focus. It's characteristic of it's fairly lightweight in its implementation, so it's low cost. But another thing that you have to have is this refresh circuit. It's just like a capacitor. Anybody we got a few engineers, so if you really don't know, ask one of them. They could probably give you a little bit of a heads up on that. So if anybody heard of a capacitor, anybody not heard of a capacitor, most of you guys, or maybe, so basically a capacitor is something that stores charge. Even like for short-term purposes, it can be thought of as a battery, if you will, but it also has other kind of characteristics for circuits that is useful. And so basically DRAM, it's just as a transistor for passing, it's just like a switch on or off, and it either loads charge into that capacitor or not. And so that's what this refresh circuit is. And so basically you have your address lines, you have your how you access the information, and you have some buffers there, and then you have control. Okay, do you have write enable or not, or you just have read access? And so those are the things that we have in terms of what's going on for memory. So that's a little bit of a heads up for that. And then the specifics is we'll get into some of these things. I mentioned this term DDR, for example, and then we'll get into some of these newer non-volatile type of memory. Actually, I've mentioned this stuff that I've been doing some research in neuromorphic computing, and there's actually some other characteristics that can be used. It's not only can be used as memory, but I talked about for neuromorphic computing, it doesn't have a von Neumann architecture. It has two things. The I/O, that's the same, but then it groups the computing and the memory together into what I call computing memory. And so how it transitions from one state to another, it's influenced by things. And so you can actually have, for example, the way that we have in our memory is like when we have an experience, it's not only just seeing the facts, but what was our emotional state, what were the contexts. And so basically how you're going to remember that event is impacted by other areas. And so those are some of the things that take place in neuromorphic computing, and they've been using other characteristics that exist for these. It's not only the end state, either having a 1 or a 0, but the things that influence whether or not it's going to record one of those states. So we'll get into error correcting, Hamming code. I'll talk about that briefly. And so this is also one of those things in the small print that maybe you didn't know about. Like for a hard drive, they actually have error correcting. So did you actually write the correct information to that one location or not? When you read, did you actually get the information you thought? And so you have a couple extra bits that help you get that information. So it gives you a higher integrity that you're not getting erroneous information. And so that's another thing that is there. So at a high level, this is I showed you a more detailed chart to start out with, which maybe it would be better to have shown this, but I just, in the greatest hits, I just pick a slide or two to warm people up to get an idea of what these concepts are about. And so this is what you have. You have your data in, and so this is when you're writing data into a memory. This is where you select the address. And I mentioned that last time, where you can be thinking of like your home address, you have a number and you have a street. And so a lot of times when you're pulling up memory, you're pulling up like everybody that lives on that block, to give that analogy. So is everybody home in each one of those houses? And so you have a block rather than an individual bit that you have that. And then finally, you have the control. Okay, if you want to do a write, I have to do write enable. Okay, that's the kind of thing that's there. For read, all I have to do, you're just sensing it. So you're not submitting data for it to store. You actually want to know what that state is. And so for dynamic RAM, which I mentioned, and I'll have a detailed chart here in just a couple of charts, it literally needs to be refreshed on a regular basis. SRAM, which I'll talk about shortly, doesn't. It has more of an enduring factor in the way that it is able to handle that. Well, we'll see this in a couple different ways, but here are some categories of memory. First of all, RAM. I think most everybody has heard that term. You almost can't avoid it if you have a computer. It's like, how much RAM do you have in your computer? Well, maybe you don't know what that is in terms of the details, but you've heard of that term. And so that's the very common thing. And so it gives the ability to read and write. Okay. And it's electronically at the byte level. It's volatile. Once you lose power, everything's gone. And so it's a little bit nicer having a laptop when you have a battery. So it used to be a power outage. If you're on your desktop and the power goes out, you just lose everything. Unless you hit the save button before that happened. And so that's one of the reasons why they have battery backups for offices. Read only is literally all you can do. You can read it, but you can't write to it. Then there's a couple special cases where you can have programmable read-only memory. And so it's a little bit more laborious, but you can do this once, only that you can write to it and then it's set. And so heaven forbid that you get the wrong thing. And so that's where they had this other type, which is a little bit more flexible, and it's erasable PROM. And so when I did my senior design project, this is what I was actually using, is I actually put all of the compiled code. I was writing in assembler language to load that into an 8085, the one step before the 8086 architecture that you guys are familiar with, and then run it. So, and then there's more flexible, that EEPROM, electronically erasable PROM. And so it gives you a little bit more hands-on. And then finally, this flash memory, like what I have in my router at home, which you guys probably have. And you could also think of an analogy like the BIOS in your computer. So that just gives you a range of possibilities of things that are out there. So dynamic RAM, DRAM, it's low cost, and it's really a nice workhorse that is in most of the memory that you have. Your RAM for your computer, it's going to be made out of DRAM. You might remember that pyramid chart that I've shown a couple of times about memory. Let me see if I can go back without confusing where I'm at here. So this is grouping it together. We'll have another chart and this chapter that will show it in a slightly different way. But let's go back to where we were. So this is a chart that once again, the engineers probably have seen transistors. The way I've done this class, bless you, is I kind of minimize this, but this is what a transistor looks like. It's one of the ways. It's a FET, a field effect transistor. And so basically in this situation, it's just being used as a switch. And this is the capacitor. So if you turn it on, it flows charge into that, and it's going to store that charge. So what happens after you've done that? What happens with a capacitor over time? It starts to leak out that charge. So depending on the type of capacitor, it could be a short period of time. It could be a long period of time. Remember, we're talking really small. You're trying to get a lot of memory in a small area, but that's a very simple circuit. For SRAM, static RAM, this is more complicated, but it doesn't need to have that refresh circuit. It's also faster. And so there's going to be places in your architecture in that pyramid, you go up to the registers, up higher to that. This is where you want more performance. This is when you want more low cost, lots of RAM. And then if you even want more memory, that's where you have the whole concept of a hard drive, an SSD, or having a hard disk. Those are the things that are available to do that. So I already talked about the SRAM, so we'll go ahead and move on. So what are the advantages and disadvantages? So like I said, SRAM is faster, that's good. It's more expensive, that's bad. SRAM, it's easier to build, and so it's going to be lower cost. And so all of those things are used. And so in terms of an architecture, and I've tried to mention a couple things, that it continues, it's a moving target about what's happening in design of computer architectures, of where can you start to improve performance. And so when we talked about metrics and performance, I always think about gigaflops, for example. And in chapter 2, we got a chance to get introduced to some of those. And so how do you figure out what's better? And so there's a lot of variables that come into that. But basically, in general, this is where we see the advantages and disadvantages of each one of these memories. So that's RAM, random read-only memory. It contains a permanent pattern of the data. So once you've locked it in, that's it. So going back to my router that I said I would bring up periodically, you can do a factory reset. And so it has ROM that it can say, this is my gold standard. If for whatever reason, if things get messed up, you push the reset button and it's going to go back to its original configuration. And so that's typically their go-to, because they don't know necessarily what a customer might have done. And so that's one of the major steps that is utilized. And so that's a nice strategy. It's also an architecture. You have a go back to position. I have a Dell server, and so if I really messed up with the BIOS, I can always go back to the original configuration that they have stored in ROM. Same kind of characteristic. Okay, PROM I already mentioned, and so it is only write only, but literally what you would have to do for to erase it. When I did this in my senior project, it had like this little film that you put on that's on the top. It kind of looks like aluminum foil. You peel it back and then you expose it with ultraviolet light, and so that erases all the memory. Then you close it up, and then you can actually do that write only once, and it stores it into that. So I can tell you it took me a lot of times, and so I feel sorry. This is why it's really good to have a good strategy of how you're going to build, test software and hardware. And like I always talk about, changing one thing at a time and then validating it. Otherwise, you're going to be really, it can be very frustrating. You're going to get a chance to have some of that with the programming we're going to do in assembly language with the Arduino. But we're going to be doing that together, and hopefully that will help out. So that's what PROM is. And so if you make some kind of mistake, you have a get out of jail free card that you can leverage that. And then just a chart to give a comparison. The EEPROM, you had to do this more fancy thing. It's going to take more intervention. Electronically EEPROM, this is something that basically it's a built-in feature that is easier for you to do that reprogramming. And then easier still is flash memory. See, like you're going to re-image your BIOS. You don't have to pull anything out. You don't have to do any special test circuit to enable that. It's basically designed so you can have all that work. I already showed you this chart, and so this is a more complicated version of what I showed here. Very simple for a read and write, but if you talk about an integrated memory, it has to have the capability to do both of those. And so that's what is laid out here with a complexity. And here we're talking about a specific size. And so 16 megabit of DRAM, so 4 megabit times 4. So there's 4 modules of the same. You put them all together, just like you stick in 2 sticks of RAM to give you a larger contiguous memory. It's the same thing, just you have things that are modular within a chip that you can be leveraging. So we're not really talking too much in the package level, but say we'll see this a little bit when you're starting to play with your Arduino. I think I showed you a schematic as well as more of a wiring diagram, like a picture of what it would look like. So this is just giving you an idea of what that chip would look like for an EEPROM, and also just for a regular bit of RAM. RAM used to come in these kind of packages, an integrated circuit. Now we're more familiar with the stick of memory that you stick in. And so, but if you looked on that stick, you would see little chips that are soldered onto the board. And so it's just another higher level aggregation of something that may be familiar to you. So this is just getting into some more of the details, and I may just skip over this just to give you this higher level perspective of it. And so we have this memory address register. So ultimately, you're thinking about how the CPU is going to be communicating with the memory, how the I/O is going to be communicating with the memory. And so these are the kind of things that are stuff that you want to make sure that you define. So I think that's enough to give a little bit of a sense of that. So interleaved memory. So sometimes you can have bleed over, like this can happen like if you have information going on a wire. The last thing you want to have is that information to couple to another wire. Not in my senior project, but earlier, I think I might have told you this. I had like, there's a TTL transistor logic chip called a 555, and it's basically a clock, an oscillator. And so what I was trying to make was a digital metronome. I learned how to play guitar in college, and so that was something I thought would be really cool. But I wanted to make it nice and small. So I didn't have one of these wiring boards. And so literally there was another way that you would have to wire it manually. You didn't have to use solder, but there was a little way that you could put these little chips in, and then you could start wiring that all together. And I just started to cram it into a small little box. And so literally it was quote, you would think it would work, but what was happening, perhaps one or two of those wires were crossing, so it was getting a short. And also this idea in the context of what I'm trying to point out here, getting that information coupling from one wire to another. So there's a lot of layers of design that needs to be thought of for electronics, and that includes computer systems. And so that's one of the things we're having interleaved memory. So you can have like, I'm going to put all of the, just use the term odd and even, I'll put all the odd things in one stick of memory and all the even on the other. Sometimes I've heard the term of, if it's a ping pong, you go from one to another. Remember I told you that memory is slower than the CPU? And so these are the kind of strategies you can be using to help to improve performance with the liability that you really need your memory, but unfortunately technology has been lagging it behind in that versus the options available for a CPU. So these are just some of the strategies you can be using for interleaved memory that you can look over. Okay, the next idea that I mentioned briefly, the concept, the fact of, was this error correcting. And so what kind of errors you can have? Literally, one thing that happens with hard drives is you get a sector. I've used that term, maybe you might remember it. And then you have a location in that sector where you have one little divot that is storing a bit of information that goes bad. It only can be read and write so many times, and after that, it's no longer usable. That's a hard failure. And so there's ways with a hard drive that there's enough extra space. Okay, it says that real estate, that's a condemned house. Okay, you can't use that. And so it then knows never to use that memory location again, but there's still plenty of other things that you can have. A soft error is like something, the reading process or the writing process didn't go as you would expect. Maybe there was a surge in the power. These are all possibilities. And so those are the things that can be there that you need to be thinking about. So error correcting is what you're doing is you're adding extra bits to try and it's so you're not as efficient with your memory, but that is the liability. But the positive is the fact that you're going to have a lot more integrity in that information that you're reading or writing. And so this is just what we're trying to talk about here. This might be a little bit hard to follow, but I'll have this and I'll have another version of this. And so this is where it's trying to show a single bit error. Okay, so you're introducing this idea called parity. You have parity bits. And so you have 3 memory locations, and then you have parity. And so here you're assigning parity for these related to what the actual what is stored in the memory. And I don't have the exact logic of the relationship between these bits and the parity. So it might be an exclusive OR, just based on, as I was starting to think about this before class. But anyway, there's a relationship between the bits and the neighboring bits that define what a parity is. So parity is not just an exact replica. It's like it's a way of saying, say you have I'll just use a number, 100 bits of information, and maybe you have a parity for 100 bits. And so what is the total number of ones or zeros in those 100 bits? And so the parity is just, it's a higher level aggregation to say, well, rough check for those 100 bits, things look fine or not. And so this is not that large, but it's a little bit lower level, that by having a parity, I can start to determine one bit, if it's erroneous, I can fix it. And so this process of this Hamming code, it can figure out that this change, you can see up here, was 1, and it changed. And so because of the parity, first of all, you have this situation, something's not right, the parity is not right, and then you can go a little bit deeper, you can figure out where that error is. And so thus you can back it up, and things are going to work fine. So there is an increase. And so if you have so many bits, you can see this, it can be a big impact. But if you start to have a larger bit of data that are going per parity bit, you can see that that percentage can go down. And so those are the things to be considering in terms of an architecture. So this is just some more details of this. I'm just going to skip over this for now but just wanted to give an idea. So we have this chart that was for a single bit. Now we have a situation where, what if we have 2 bit errors? And the punchline is, with 2 errors, the single error correction does not work. It just gives some erroneous results. It doesn't make it better, it makes it worse. And so that's, we see like a simple scheme for a Hamming code for 1 bit that works, and that may be adequate. What if that covers like 95% of your errors? That could be good enough. And so that just gives you an idea of what you can be doing for memory. So here's these fancy terms now. Like if you were to go to, now I'd have to say Best Buy, you used to say Fry's, or Micro Center, it's in Orange County, there's not so many of those. And so you have this term like this, DDR SDRAM. Well, what does that mean? It means double data rate, synchronous dynamic random access. And so we've already talked about dynamic random access. Here we have some more things that are out there. So SDRAM, it's one of the most critical system bottlenecks when using high performance processors to interface to the main internal memory. So this is going to be a little bit more higher performance rather than just regular DRAM. And so that's what we have there. The traditional DRAM chip is constrained both by its internal architecture and it's by an interface to the processor's memory bus. Something to be thinking about, and a number of enhancements to the basic DRAM architectures have been explored. And so this is where we get this, where we are now, SDRAM or something like that with here, this R. I think that might be a typo. Sorry about that. It should be SDRAM. I'll try and fix that. So just giving you a couple ideas of the different types of memory. SDRAM, it's one of the most widely used focuses of RAM. We've already talked about this. And so SDRAM is something you're going to hear about when you go to the store and try to buy something. So this is a chart like what we saw before. You have these different memory modules that are put together to get the overall level of what you're trying to do for a specific chip. And so this is for a 256 megabit. And so that's made up these smaller bits, these smaller packages to get what you need. You have the address lines, you have the buffers, you have the control lines, all of the same kind of things that we've already had a chance to to be exposed to. So this is just some of the pin assignments that are associated with that RAM. And so you can look over that in more detail. And so here's just gives you an idea, like having a burst mode instead of just reading one bit, like I mentioned before, everybody on your block. And so you have them all coming out at once. And so that's something that you can be doing, and it takes so many clock cycles for them to come out. So you're getting, like, say, a burst length of 4. And so this is just another strategy that you're trying to figure out how to improve memory performance when you know that it is slower than other components in your architecture. I've actually had friends, colleagues that have been part of JEDEC, the Joint Electronic Device Engineering Council. And so microelectronics is the area, and let's say that you have different memory manufacturers that are trying to decide how they're going to do things, processors, some of the stuff I mentioned in terms of microelectronics. This is a body that is not any particular company, but all of these different industry partners that make these parts and people that want them, large buyers of those things, get together and try and work out agreements to make sure that things are all copacetic and they like the direction where they're going. We'll get to this in the next chart, but like to agree on the terms of what DDR1 is, DDR2, DDR3, DDR4. Those are the kind of things that they would be getting a chance to be working through. And so now that you have this architecture that everybody knows, then you can say, okay, one manufacturer that builds memory, they can build their proprietary way of implementing that. And they're trying to get them folks to buy their memory versus somebody else's, but in these type of consortiums that they work out those details. So then we have, so you have the effective memory data rate that's going out, and then you have what's going inside. So using some of these tricks to try and make it effectively faster when it's going to the connection going with the CPU or the input and output. And so this is just some of those details, and you can see that these numbers are getting larger. And so this is the thing that you'll hear if you saw some of the data sheets of what you're looking for. There'll be a range for CPU in your motherboard. It would say that you need to have a front side data bus data rate of a certain point, so 1600 or something like that. And so that's you might be able to, if you're like here, you might be able to use DDR3 or DDR4. But if you want to go to the as fast as you can, you like to be going to that DDR4. And so this just gives you an idea. So you can see how each one of these renditions, you're basically doubling it. And so like the DDR4 is 2 DDR3 put together. And so you have another way of aggregating that. And the term that's used is called a mux. And so this is how you're able to double effectively what you're able to get. And you're going to have a range depending on how well you utilize each of these elements. So I mentioned a little bit here, and later in the course we'll get into the specifics about hard drives, but now you're starting to get some more insight into how memory is aggregated. So you buy the sticks of RAM, you have chips that are soldered onto that. In each of these chips that you would look at, you have various ways things are aggregated. And so there's multiple ways of starting to get smaller areas of microelectronics working together to do one particular thing. I've covered a lot of ground. Let me just pause for a second to see if there's any comments or questions that people have. Okay, I think we got a couple folks online, so if anybody does have a question, you can just go off mute or put it in the chat, and I'll be glad to take your questions. So those are some of the big highlights that I wanted to be mentioning. Here we have an IBM server type of design, and so this is a storage controller, and so they have an L4 cache, and so you have L1 through 3 close to the processor, and then you have off something that's another layer for caching that we can see here. And so that stuff, just to give you an idea. And so the use of eDRAM is one of the things that they're leveraging in that application. And finally, flash. Okay, flash memory. I mentioned my example of my router. I was able to flash it, got it to work. Unfortunately, there were some other issues I wasn't able to figure out. So I just went ahead and returned that router, and the one I'm using at the moment is pretty good. And then it's kind of a gap filler. And then I just found out last night that they're shipping this other one, which not only has Wi-Fi 6E. I don't know if you've heard of that. There's Wi-Fi 6, Wi-Fi 6E. This actually has the capability for the next standard, which is something called Wi-Fi 7. So it's supposed to be even higher. And in terms of the wireless data rates that you can sustain with that type of equipment. So just some different types of how things are actually fabricated in the microelectronics. I'm not going to focus on this, but you can look over that in the textbook. But one thing I will point out is here we have these two competing technologies, a NOR or a NAND. I said before that you could create everything that you want for processing with using NAND. You could also do that with a NOR gate. It might take more gates, but it's actually in the long run, it's actually going to be helpful. But this next chart, I think, might be instrumental to give you an idea. I'm used to calling these spider charts. And so basically, the bigger the blob in the center, that's better. And so you can see that for a NOR, although it does work, but you can see that the blob for a NAND is actually better. It's bigger. And so here's like an example where maybe it's not performing as well, but in most of these other situations, we're seeing that this blob is bigger. And so kind of in a very high level point of view, that just gives you a sense of why things tend to go in the direction of using NAND versus NOR. As I recall, the NAND gate takes the fewest transistors to actually create that. And so that's another rationale behind that. Okay, so I'll have this chart, and then the next chart I'll kind of go into this in a little bit more detail about. Here we have some more terms. We're not talking about DRAM or SRAM. We're talking about some new innovative ways of how memory is being stored. And we're seeing another pyramid. So we can see how DRAM, one of the things that they use is something called PCRAM. And I'll define that term in a minute. Resistive RAM, RERAM. This is something that, say you have a solid state drive, that would be something you would have here. And then this SRAM, here is something that has higher performance, and a way that you could be implementing that for SRAM. So this kind of exposes some of those terms that I try to spell out in more detail. So it just goes to show you that there's a lot of different type of phenomenology that's out there to leverage. And so physicists, engineers, and computer scientists, and that's like our first cousins, if you will. And a lot of times we don't do that because you have to get into the how materials actually work. And so something like a spin transfer torque, and I could share some articles that talk about these types of things, but there's a way that you can have these two types of outcomes that either makes it so it's either a 1 or a 0. And so maybe instead of just applying a current in a way that you might have thought of for one type of implementation of memory, it's a different. I find it a little bit easier to get my head around something called magnetic RAM. And so basically it's like having like a magnetic bead. It used to be real old style memory, how they did it, and it is either in that magnet was either one kind of orientation or another orientation. And that's how you flip the memory, was by changing that orientation. And so that's what we're seeing. Instead of having like a little magnet, the spin transfer torque puts it this effectively, just think of that in terms of a magnet. It changes it one orientation in that little cell, that little memory cell. That's one area that's out there, one type of memory. Another is something called phase change RAM. And so that's what we saw here, this thing here. And so this is somewhere in between. And so STT-RAM or MRAM is going to be higher performance. PC-RAM is going to be somewhere in between. And something down here, resistive RAM, this would be something that would be a lot more ideal for use in large areas of memory where you're trying to cover a lot of ground. And so say in a SSD, that might be an area where that would come in. Okay, well, that's a lot of information that I've covered, but hopefully the way that we went through it was helpful for you to get the big picture of what we're trying to think about for that. Any comments or questions